The share of electronic cars in the total car industry is rapidly increasing. This happens because the electronics used for electric vehicles is getting of better quality for less money. Therefore, without spending a lot of money, you can buy the more environmental friendly variant of the powertrain in the car of your choice. As people like to put out a good image of themselves to the outside world, in combination with seemingly healthier car, it causes a rapid increase of electric motorists. What an electric car loses on battery pollution, it gains with its more economical driving. Therefore, it is important to keep improving the economical side of driving. This is what our employee EPE vehicles aims at. They announced their first full electric car, and our team was given a scaled down prototype to use for testing and improving. Where we will show off our improved model around the test track. We took our model through 3 experiments: the rolling resistance test, the aerodynamic drag test, and the dynamometer test. After we had done our test, we had to gather our results and in order to use for a good strategy for going around the test track as good as possible. Another thing the model car needs for a good completion around the track is a speed measurement system, so the driver can stick to the traffic rules and knows when he's going too fast. The car needed to have the innovative feature communication with a toll booth. We call this the toll payment system. This basically means the car will stop and pay its toll for you. All of these things will be spoken about in this presentation.
Why are the speed measurement system and toll payment system important? It's of great importance to gather data of the car during development to ensure it's suitable for the consumer. The time when the car goes around a certain track is very useful because the average energy consumption over a certain distance can be calculated and adjustments can be made to reduce the overall energy consumption. Furthermore, another aspect that contributes to an efficient car is the driving strategy, combined with the optimal speed, should make the car more energy efficient. That's the goal of this project. First, I'm going to describe the speed measurement system. The speed measurement system consists of 4 RGB LED bars, each having 32 LEDs. The lighting system is going to display the driving speed and will use light patterns to indicate optimality, which corresponds to a certain driving speed. The color red will be used for overspeed, green for the most optimal speed, and blue when the speed is too low. Time is also an important piece of data here because the speed at any given time needs to be calculated, which is tied to the number of complete revolutions in a minute. But for our specific case, the formula is different. We have to take into account the amount of magnets on the cogwheel, the time between 2 signals, and the gear ratio. The speed intervals and optimal speed should prevent the driver from braking and accelerating too often, as it will result in energy loss. However, this may change according to the driving strategy. The toll payment system consists of 2 components, the car side, which is on the car, and track side, which is along the tracks. First of all, when the car drives past the track box, which is at the beginning/end of the track box will send an infrared signal to the car. The specific frequency of the signal is 40 kHz to prevent disturbances. Second, the infrared receiver on the car receives the signal and will decode the signal, which is binary and 2-bit. Third, if the value of the signal is equal to 1, the car will send its identity to the specified trackside address through the radio frequency transceiver. If not, the infrared receiver resets so that it can receive another signal. And also here, time is also an important factor regarding energy efficiency. The track box is at the beginning and at the end of the track, and the time measured, with the time measured, we can calculate the total energy consumption. To conclude, to keep measure of the speed at any given time, the speed measurement system must keep track of the rate revolution per minute. The speed measurement system and the driving strategy should prevent the driver from wasting too much energy, while the toll payment system is useful for the total energy consumption.
Hi, I'm Marcus, and I will be talking about the aerodynamic aspects of the car. I will be telling you about how and why it was conducted, what were the findings, and how we translated the gathered data into lowering our test car's energy consumption for the challenge day. Why are aerodynamics important? The importance of an aerodynamic body on a car is often overlooked by the average consumer. But the aerodynamics of a car play a huge role in minimizing fuel consumption and lowering the road noise. Our goal with this experiment was to minimize the aerodynamic drag of our test car, resulting in a lower energy use. The more aerodynamic a car is, the lower its drag coefficient is. Drag coefficient is a term used to measure resistance forces in a fluid environment, such as air or water. To calculate the air drag coefficient, we use the formula you can see on the screen. For the calculations, we also had to measure the frontal area of the car before doing our calculations and tests. Our test took place in the TUE wind tunnel on the 4th of December. Our goal with the experiment was to find out the optimal speed and setup for the test car for the minimal energy consumption. For the experiment, our test car was put on a fixed wooden plate in the wind tunnel, and the test was conducted at 5 different speeds, ranging from 10 to 30 kilometers per hour in 5 per hour increments. During testing, we tried different setups for the car's bodywork. The first test was done without any spoilers or splitters or additional modifications besides the bottom plate. The second test was done with the front splitter mounted, the third test with the rear spoiler mounted, and the last test was done with both the front splitter and the rear spoiler mounted. The reasoning behind doing the test with different setups was because from previous knowledge, we assumed that the car will have a lower drag coefficient without any spoilers on, lowering the drag coefficient but decreasing the downforce. And what were the results of our wind tunnel tests? The first part of our results are the values that we got for the air drag coefficients. We found that the lowest air drag of our car is with the front splitter and rear spoiler both attached, followed by just the front splitter attached. And the highest coefficient can be found with just the rear spoiler on, meaning that the biggest air resistance will be in that setup. As expected, the air drag grows exponentially with the speed increasing. That growth can be seen on the graph, the left graph. The second part of our results are in regard to what speed the car is most aerodynamic at. Our test shows that the optimal speed that we tested for was 30 kilometers per hour, which was also the fastest speed that we tested at. Even though the optimal speed would be keeping it at 30 kilometers per hour constantly, it's not possible for us to drive around the narrow course at this constant velocity.
In our model car, the energy consumption can vary. The model car is not an ideal powertrain, which means that there are power losses and that not all provided power ends up at the driven wheels. There's a certain efficiency of the powertrain that limits a certain output to be lower than a given output. Using a dynamometer, we measured the car's power output with a given input to find this efficiency. During 3 different tests, we measured the power losses in the powertrain. In the first test, we measured the speed dependency of the rolling resistance on the roller of the dynamometer. Which you can see in the Sankey diagram here, with as the power loss, the peer rolling resistance, and as output, the power to the wheels. In the second test, we measured the power losses of the powertrain and the power losses of the motor, which you can see in the Sankey diagram over here, with at first the power losses of the auxiliary losses, then the motor and powertrain losses, and then the rolling resistance losses, which result in the power to the dynamometer of the wheels, the rotation of the wheels to the dynamometer. In the third test, we measured the auxiliary losses of our model car in an idle state condition, which means that the only power from the battery which are delivered are the auxiliary losses. The total power balance of the dynamometer test will look as follows. That means that the total power is the power from the battery minus the auxiliary losses, minus the motor losses, minus the drivetrain losses, and minus the rolling resistance losses. The ultimate goal of the experiment was to measure as precisely as possible efficiency of the car during several speeds. This can be explained in this formula, which is the efficiency is the output power divided by the input power. When you write this out, you will get the power from the dynamometer, which can be described by the road load multiplied by the speed of the car, plus the power from the rolling resistance, which we measured in the first test, divided this by the power from the battery, which we measured during the second test, minus the auxiliary losses, which we measured during the third test, which is also a constant. By using this formula, we created an efficiency map of our model car, which you can see in this figure over here, with on the x-axis the speed of the car, on the y-axis the force, the road load exerted on the car, and on the z-axis the total efficiency by using this formula.
The wheels of a car are not completely round, which also create resistance when driving. This experiment gathers the amount of resistance that is caused by the offset in the tires. This offset is caused by the weight of the vehicle pressing the air into the side of the tire, like you can see in the picture here. Like you can see, with this phenomena, the tires contact area with the road is not symmetric. It needs an ideal shaped form to keep momentum going. In order for the car to keep her momentum, there has to be a force delivered to counteract this resistance, which uses energy. More resistance means more energy used to counteract this resistance. Thus, minimizing the rolling resistance is one of the necessities to maximize the car's performance and efficiency. Another part of the rolling resistance is the traction loss between the wheel and the surface. This will, of course, differ for different road types. Therefore, we conduct the rolling resistance test on the same surface as our test tracks consist of. The goal of the experiment was to determine the rolling resistance coefficient of the car model to calculate the amount of energy that got lost each distance the model drives. The experiment was conducted in two ways, with the drivetrain connected to the wheel axis to measure the total losses the car experiences when coasting down from a slow enough speed that the aerodynamic drag can be neglected, and a way where we let the tire resistance only slow down the model. First, we put the model car on a ramp. The gravitational force will give the car its acceleration until the ramp gets horizontal. From there, the rolling resistance will cause the car to decelerate. The measurement of deceleration was done by Arduino Do and the steering servo that keeps the car moving straight. Using the formula in the PowerPoint, we calculated the rolling resistance coefficient. We see here that it's a linear formula to check if we did the test correctly and to simultaneously check our calculations. The received data was plotted in these graphs. Like you can see in these graphs, the result is in a linear line. The three results are put next together to see the overlap. As you can see, the line states that the decelerations were linear, thus our formula and our calculations are correctly connected. With g being constant and having measured the acceleration variable, we only had to implement it and we got this answer. The rolling resistance coefficient is 0.0383.
The goal of the time-to-wheel analysis is to determine the losses of all the components in the vehicle at every speed. Power losses occur on different bars in our model car, and we tested this during 3 different experiments. In the wind tunnel, we tested the power losses from the air drag, which you can see in the picture and as the blue line. The power losses from the rolling resistance is you can see in the orange line, and it is a constant. When you add the forces of the rolling resistance to the aerodynamic drag, you will get the total tractive force exerted on the car, which you can see in the picture. As function of the velocity and force. You can see that the gray line gets more steep when the speed gets higher, so the lower speeds will always cost less power. For each combination of speed and resistance, the electric engine uses a specific amount of power, which is seen in the following picture. in the figure is shown with the lines and the colors to make it more clearer the power usage of the car. For example, at a speed of 15 kilometers per hour and a force of 11 Newton, the car will use approximately 103 watts. The black line on the bottom of the graph represents the total resistance forces that were the result of our test. And so this line visualizes the amount of energy we will maximally use when we drive our car with all the resistance applied.
Now, finally, for the driving strategy. An efficient driving strategy is definitely the key to energy conservation. Studies have shown how unnecessary braking will dissipate the kinetic energy from the wheels into heat in the brakes, resulting in energy loss. So that's the same case with hard acceleration. Since our goal is to use as little energy as possible, on our test run, we have adapted a driving style that will take those factors into account. After analyzing the schematics of the test track, we have adapted a driving style that will minimize excessive braking and acceleration while still following the traffic rules, meaning the speed limit will be observed to not exceed nor annoy other drivers who might be on the road in real life in real driving conditions. Having received the necessary data from the tank-to-wheel analysis, we are able to conclude a couple of things. Going faster uses more energy, and air drag is not a big factor while driving slow. As we won't drive fast, it can almost be neglected. Rolling resistance is a constant. The speed that we choose has to stay low as possible, which is according to the rules of the Dutch road network, half of the speed limit. As in the city, the speed limit is 50, so our speed will be 25 kilometers per hour for now, as we haven't really picked a certain speed yet. These methods were concluded from our tests. The optimal speed for driving can be derived from an efficiency map that takes the aerodynamics, rolling resistance, and dynamometer tests all into account. I hope that everything discussed was clear and understandable. We have clearly worked hard on this project, and we are waiting to see if the work has paid off on Challenge Day.